The curiously recurring template pattern is an idiom in C++ in which a class X derives from a class template instantiation using X itself as template argument. More generally it is known as F-bound polymorphism, and it is a form of F-bounded quantification. History: the technique was formalized in the 1980s as F-bounded quantification. The name CRTP was independently coined by Jim Coplian in 1995, who had observed it in some of the earliest C++ template code as well as in code examples that Timothy Budd created in his multiparadigm language leader. General form. Some use cases for this pattern are static polymorphism and other metaprogramming techniques such as those described by Andrei Alexandrescu in modern C++ design. It also figures prominently in the C++ implementation of the data, context and interaction paradigm. Static polymorphism: typically, the base class template will take advantage of the fact that member function bodies are not instantiated until long after their declarations, and will use members of the derived class within its own member functions, via the use of a cast in the case of multiple inheritance. For example, in the above example, note in particular that the function base interface, though declared before the existence of the struct derived is known by the compiler, is not actually instantiated by the compiler until it is actually called by some later code which occurs after the declaration of derived, so that at the time the function interface is instantiated, the declaration of derived implementation is known. This technique achieves a similar effect to the use of virtual functions, without the costs of dynamic polymorphism. This particular use of the CRTP has been called simulated dynamic binding by some. This pattern is used extensively in the Windows ATL and WTL libraries. To elaborate on the above example, consider a base class with no virtual functions. Whenever the base class calls another member function, it will always call its own base class functions. When we derive a class from this base class, we inherit all the member variables and member functions that weren't overridden. If the derived class calls an inherited function which then calls another member function, that function will never call any derived or overridden member functions in the derived class. However, if base class member functions use CRTP for all member function calls, the overridden functions in the derived class will be selected at compile time. This effectively emulates the virtual function call system at compile time without the costs in size or function call overhead, at the disadvantage of not being able to make this choice at runtime. Object counter: the main purpose of an object counter is retrieving statistics of object creation and destruction for a given class. This can be easily solved using CRTP. Each time an object of class X is created, the constructor of counter is called, incrementing both the created and alive count. Each time an object of class X is destroyed, the alive count is decremented. It is important to note that counter and counter are two separate classes, and this is why they will keep separate counts of X's and Y's. In this example of CRTP, this distinction of classes is the only use of the template parameter and the reason why we cannot use a simple untemplated base class. Polymorphic copy construction: when using polymorphism, one quite often needs to create copies of objects by the base class pointer. A commonly used idiom for this is adding a virtual clone function that is defined in every derived class. The CRTP can be used to avoid having to duplicate that function or other similar functions in every derived class. This allows obtaining copies of squares, circles or any other shapes by shape Ptr clone. Pitfalls: one issue with static polymorphism is that without using a general base class-like shape from the above example, you cannot store your derived classes homogeneously, as each CRTP base class is a unique type. For this reason, it's likely that you'll want to inherit from a shared base class with a virtual destructor, like the example above. In other languages, in Java and the .NET framework, it is common for a class to extend generic superclasses and interfaces having that same class as a type parameter. Usually it is done to make sure that method parameters and return values are correctly typed as their declaring class. For example, the following Java class implements the generic interface comparable from the standard library. This ensures that no attempt is made at compile time to compare an item to something that is not an item, such as a string. Unlike C++, a Java class not only cannot extend the same superclass twice with different type parameters, but it also cannot implement the same interface twice with different type parameters. For example, the class item above cannot implement both comparable and comparable. See generics in Java radian per second euro problems with type erasure for more information. See also, Bartone Euro Nachman trick, F-bounded quantification. References